So the first example we're going to look at is example 5.8.11. That's on your book, page 318. And so in this problem, we have two drums. They're co-centered, and one has a smaller radius. Let's call that r, small r, little r. And the outer disc or drum has a large radius with as r, capital R. And here we have a box A, and a block B. Those have mass MA and MB. And this drum, let's call it, this whole drum has a mass capital M and is fixed at point O. Okay, and both A and B are connected with the rope, and the rope is connected with the drum. And we can call this point, let's give a name, A, and this connecting point B. And we write down all the given conditions. So this problem is given both MA equals 10 kilograms, MB equals 30. Now we know the radius of the small drum, which is 0.2 meter, and big R is 0.4 meter. And also we know another, if you read the problem statement, it says, let's see. Okay, so it's given KO equals 0.25 meter. So this EO here is a new concept we haven't touched. One of your homework problems have this as well. So this is called radius of Euratio. This KO. That's the name of KO, radius of Euratio. And what does it mean is it shows how mass is distributed at a certain location from the point where the rotation is about. So the more mathematical expression for this radius ratio is IG, no IO. Let's see. Let's follow this here. Since here we use the letter O, that's the point where this drum is fixed. So let's follow that. So the corresponding IO, which is the mass moment of inertia about point O of equals M times KO square. So this KO is the radius of ratio. And so this tells you, as long as you know this KO, the radius of ratio, you're able to use the mass times this KO square to find out what is the moment inertia at that point. And you will also see, we can change this through M to the other side of the equation to get expression for KO as well. KO equals square root IO over M. That is something new. It's also in your homework. So in this class, whenever you see this KO or KG, no matter what letter is that, just think that's the information can tell you what is the moment of inertia about that point, the same point. Okay, so those are all the given conditions. In this problem, trying to find out what is the alpha, which is angular acceleration of the drum. And when it's released from rest. And this release from rest is a keyword. Whenever you see that, that means right at that moment, when you release everything, the system has zero velocity or zero speed. Okay, now let's look at this problem. With all the given informations, and what we're trying to find is alpha. And this is a solid, rigid body kinetic problem. And how this problem is different from the previous example is that if you count how many masses we have, here in this problem, we have A, we have B, and we also have this disk. Both of them, they all have masses, right? So this is a multi-mass problem. And it's similar with the problem we did in chapter 4, how would you deal with problem with multiple masses. So let's take a look, how do we solve this problem? So the steps to solve this problem, it's the same. Use the 6 steps approach. Start with step 1 and 2. Free body diagram and coordinate system. And since we have multiple masses, and so be careful here, when you try to draw a free body diagram, I would suggest you to draw a free body diagram for each mass. So that's kind of a rule, just follow whenever you have multiple masses in the problem. Draw the free body diagram for each one. It doesn't take a long time, but make sure you get everything. So let's start with the first mass, which is our drum. We have an inner drum and an outer drum. And we know the drum itself. This is the center of mass at point O. The drum itself has weight force. Also at the center, point O, if you look at the problem statement, O is fixed there, right? The whole drum is rotating about O. So we need to have reaction force there. So we have a Ry and Rx. Besides weight force, reaction forces, and we also know the drum is attached with 2 cables. One is connected. I was hoping that. Excuse me. Any questions? Okay. I heard someone was talking. Okay, never mind. So we know the 2 cables are connected with block A and block B. So the cable will create a tension force on the drum, right? So we need to have 2 tension force. Let's use a different color here. And you should have this tension force. Let's call this TB. So on the outer drum, we have another tension force. It's going down. Let's call it TA. Make sure you add vector notation, all the forces. And do we have any other forces for this rigid body? I think that's it. All right, now we're done with free body diagram just for the first mass, which is the disk. And now let's look at the block A. Let's take block A. And we know block A has mass. Start from its center mass, W, let's call it WA. The tension force is pulling it up. Just TA. Similarly, we have another block B, with force WB and tension force TB. In terms of coordinate system, I think we can just use I and J for this problem. And so whenever you have a system that contains multiple masses, pay extra attention for the force they shared between 2 masses. For example, here, I have TA, both of my the first free body diagram, the second free body diagram. And as you probably can see, on these two free body diagrams, my TA force has same magnitude but opposite direction. You can also see that from my tension force TB. Okay, so that's how we finish step 1 and 2. And step 3 is to list all the forces in vector form. And same thing, since we have 3 masses here, so I would suggest you to list the vector form of all the forces for each rigid body. Okay, here we have T, A. TA, it's on negative J direction, so it's negative TAJ. And TB, positive TI direction. We force, it's a negative MG on J direction. And RY, we don't know what's the value for RY, but we know our Y is on J direction. And our RX, it's on I direction. 1, 2, 3, 4, 5 forces. Now we're done with first rigid body. And for the second rigid body, TA, now our TA is pointing upwards. So it's positive TAJ. And our WA, it's negative MAGJ. Now let's look at block B. TB, since we had a pulley there, it changed the direction of the tension force. Now our TB is pointing to positive J direction. Our WB was negative MBGJ. Okay, so that's how I finished the step 3, this forces in vector form for each rigid body. Now let's move on to step 4. Step 4 is to list the acceleration in vector form. So for the first rigid body here, this disk, and we want to list this acceleration for this big MG. Remember, in this chapter, all the acceleration should be the acceleration of this mass center. So I would add it. In this case, will be O, since the center mass is O. So what is AMO going to be? Acceleration, oops. Sorry, there's something wrong with this app. Let me restart it. Okay, so what is AMO? What's the acceleration of the disk of the center mass? If we go back to the problem statement, the whole drum, the drum is fixed at point O. So it can rotate about point O, but it couldn't move any directions, right? So that tells us acceleration of MO is 0. Hopefully you can see that. And let's look at the acceleration for A. Block A, let's go back here. Block A, both A and B are hanging from the rope, so it can only move up and down. So that tells us AA only has J components. Let's call it AAJ. AB only has J components as well. Okay, now we finish step 4, right? Acceleration in vector form for each mass. Now step 5, apply Newton and Wheeler's second law. So Newton's second law is sum of all the forces is ma. That's okay. Let's get rid of this. That's a general form. Okay, so let's apply this equation, Newton's second law, to each mass. For the first free body diagram here, we can apply Newton's second law to this since we have those forces on I and J direction. So then you can end up with the equation I and J. So on I direction, all the forces we have are TB, right? TB, look at what we have in step 3. What other forces in I direction? That is this Rx, TB plus Rx, and the sum of them equal to MA, since we don't have acceleration for AMO, so that's 0. Okay, now let's look at, move on to J direction. We have TA, just negative 2A, minus mg plus ry, and sum equal to 0. All right, now we have 2 equations just from the first mass. And let's look at this for the second mass. And what we end up with for block A is all the forces for block A and B are on J direction. So we only should have equations on J direction. For A, it's going to be TA minus MAG equal to, or leave this blank here. For TB, it's going to be TB. Right. That's little b, little a and little b minus mbg equal to. Okay, so that's, leave this 2 as blank as a question for you. If I write 0, would that be right? So sum of the forces on J direction is 0 for both block A and B. Could someone tell me, is this right or not? I'm going to call someone to answer this. How about Isabel? Can you tell me if can we write sum of forces equal to 0?
No.
And then how should I correct this?
It should be for TA minus MAG. It should be M times the acceleration in the J.
Yes, so that's correct. 0 is not right. This is, if you have 0, that means you are still in statics. This is dynamics. So tension minus the MAG not necessarily equal to 0, because that you need to count for the acceleration MA. So equal to MA times AA. So for B equals MB AB. Since we have acceleration for both A and B. Okay. So I think that's the common place students can make a mistake. Okay, now we did Newton's second law for each mass. How about we still have another equation we can use, which is Wheeler's second law. We can use sum of all the moment equal to the equation we learned, right? So it looks like this. And there's some other terms. And usually we can pick the special case to get rid of the second term to make second term equal to 0. So in this case, if we can pick center of mass center as the point we analyze moment, then this is the equation we can use. So in that case, you need pick center mass. The corresponding I should be this moment inertia about the center mass. And like I said, before you use this equation, find which point you're going to find moment about, and also find what is the positive direction. So define this is our K, and the positive direction going to be positive, which is counterclockwise. Okay, so you're going to use this Wheeler's second law for each mass. And let's do that for the first mass. In order to do that, you need to go back to the free body diagram. The center mass of this rigid body is at the center point O. And if we use that point O to analyze our movements, and we can get rid of Rx and Ry since they're both passing through the point O, and as well as this weight force. So at first sight, we know that these three forces would not cause any movement, so we don't have to worry about them. The only two forces will cause movement about point O would be TA and TB. So, and TA cause a movement about O that is clockwise, and TB would cause a movement about O that is counterclockwise. And the distance between T and TB to O would be small r and little r and the capital R, respectively. So let's write that out. Sum of all the moment about point O gonna be TB. Let's start with TA. That's positive. TA times big R minus TB small r. Let's double check. Yep. Distance between TB and O is small r. Between O and TA is big R. And they were equal to I O alpha. Okay. And here we get our first equation. Let's see that. Now first equation, we already have two from I and J. Now we have third one here. Now let's keep working on this. We can apply it with our second law to, let's highlight this, to the second mass as well. If we look at A, and the moment about center mass of A is what? We only have two forces that both pass through that point. Therefore, we don't really have the sum of the moment equal to 0. That'll be true for both A and B. So if you want to write that, that's kind of pointless. That's equal to 0 equal to I A G alpha. This can be goes to I, B, G, alpha. This two equation doesn't tell us anything. They're useless here. So we don't, I think the most helpful equation going to be the equation, let's highlight here and here, and as well as this equation. All right. Now let's look at all the equations we have. We have three equations. Let's count how many unknown we have. TB, we don't know. RX, we don't know. TA, nope. We know M, we don't know what is RY. And so we have 1, 2, 3, 4, four unknowns. When you count how many equations we only have three equations. So that tells us we need more equations. Usually when you need more equations, and we need help from kinematics from chapter 2, the rigid body kinematics. And so how can we apply chapter 2 here? What we learn in chapter 2. So if you look at our drum here, okay, look at this rigid body, and this kind of, you can see that as disk is fixed at the center point, and if we call the acceleration at this contact point like AA, and let's call the acceleration from this cable AB, and both AA and AB, they're in the same rigid body, and this rigid body is fixed at a fixed point O. So we do have an equation in chapter 2 that describes the relationship between two accelerations, the points of two accelerations. All right, so we can use that. So let's look at AA. The equation, this is the equation from chapter 2. So AA, that's one point A, and another point we're going to look at point G, since that's a, in this case, going to be point O, since that's a point that's fixed. And AA equals AO plus, hopefully you still remember the equation, alpha, and which is angular acceleration, cross product RA/O. We have another term here. This minus omega square RA/O. So that's one equation we can get, right? Another equation is we can do the same thing for B. B to O, alpha cross RB/O minus omega square RB/O. If you look at these two equations, this is like this equation we learned in chapter 2. And do we know this AO? We did something for AO, right? That's our AMO here. Since O is fixed there, therefore this 2 goes 0. And if you look at omega, what is omega? Omega is the angular velocity. And if you come back to the problem statement, everything released from rest. So that's a hidden information, tells us omega equal to 0 when we release the system. So we can get rid of this term here as well. And now we can simplify this. We can simplify AA. A to alpha, its angular acceleration that's on K direction. RA/O. Let's go back to our free body diagram. O is the center, A is that point, RA/O. So A/O, that is starting from O pointing to A, that is negative I direction. So you end up with alpha K cos negative small r J I direction. And do the cross product, you end up with K I will give you positive J. Right? So you end up with negative alpha RJ. That's what you get from the first AA equation. And from the second equation here, you can find AB. Because alpha K cross product RB/O is going to be start from O pointing to B. Oops, I think I made a mistake here. Let's go back check. From O to A, that's big R. From O to B, that's small r. So I need to change this. That's negative r. Here we have small r, rj. And the cross product, result of cross product going to be negative I. Negative alpha ri. Okay, so by applying what we learned in chapter 2, we can create 2 more equations. We have 2 more equations here. Let me highlight the equation. And now we should have enough equations to solve all the unknowns we have. The rest of the problem is just algebra, and that's the hardest part. But fortunately, I'm not very strict on how to get the result, the final result. I'm more care about if you know how to follow the steps to find the necessary equation to solve this problem. So what you can do is, in order to solve this problem, you can use the two new equations to find the expression for alpha, then plug them into this equation here and try to solve what is alpha, since that's the alpha is something we're trying to find. Yeah, we're trying to find alpha when this drum is released from rest. And something to highlight here is this IO. Let's use a different color. This IO here is not given directly, but we mentioned this radius of ratio tells us what is IO. Where did it go? Yep. So IO can find from this equation. So that, use that. So IO equals M. That's the mass for the drum. And times K whole square. Okay. Now you should have all the equations to solve this problem. Let me just show you the final solution. So alpha, you plug in everything, end up with something negative 0.84 something radius second square on K direction. Okay, and this is example. Now you'll find out one of the homework problem is very similar to this example. So if you run into any difficulties, you can come back, refer to this example. All right. So any questions on this example? We have 13 minutes left, then I think we can go through one more example. Another example is also on your book. That's example 5A12, page 319. In this example, we have a disk. This disk has an inner circle and outer circle. And this disk is on a rough surface. So there's no slip condition. This is another, we learned no slip condition previously, right? So whenever you see no slip, that tells you a lot of information and also give you the sense that if there's no slip, that means it is a rough surface. It should have friction. And the contact point is C. And the smaller disc here, its spoon here is connected with a rope. And the force is applied to that rope with the angle theta. And we know the center mass. We know the radius, small r, and the big R. So those are the given conditions. We know r, small r, we know the mass, we know theta, and we also know force. And what we're trying to find is, we're trying to find angular acceleration of the spoon, which is alpha. So I just saw the question from Adam from last example. Yes, all the highlighted equations should be enough to solve this problem. And also, don't forget, you have equations from the acceleration as well. This. Okay. So for this example is pretty similar with FA11. We're both trying to solve what is alpha, which is angular acceleration. How to solve this problem? And the same thing. It's follow the 6-step approach and find all the equations you may need. And the only difference for this problem is if you count how many rigid body you have, you'll find we only have one rigid body, which means you just need to have one free body diagram, and you don't have to consider other masses. So that's probably it's easier than the last example. Okay, that's step 1, 2. Free body diagrams. Free body diagram includes you have weight force coming from the center mass, and should have a normal force as well. And don't forget, there's a friction force there. So we have a force with the angle there. Those are the 4 forces you should have in this problem. Coordinate system going to be just J, Ij. Oops. Excuse me, I think this app is crashed again. Okay, so now we have step 1, 2. Step 3, and all the vector form of the forces. With force negative mgj, normal force going to be nj, friction force it's negative fi. And in this problem, we don't even know what is the friction coefficient. So if you write that as mu n, that's kind of increasing more unknowns. So we don't know too much about the friction coefficient. But we can write our f as both I component and j component with that given angle theta. So the x component, the I component of f gonna be f cosine theta I plus f sine theta j. That's step 3. Step 4 is acceleration about the center point, center mass. If we look at this our point G, center mass, how this spoon gonna move, what's the acceleration of the center mass? If you look at this whole spoon, the rigid body, it can only move left and right, right? So the acceleration only has I components. Okay, that's step 4. And step 5, apply Newton's second law and Wheeler's second law. Sum of the forces equals to ma, and this can be broken down to I and j. On I direction, we should have f cosine theta minus ff, which is a friction force, is equal to mag. On j direction, we have f sine theta minus weight force. Oops, excuse me. We shouldn't have that vector notation since here we're already break down to I and j plus normal force equal to 0. So now we have 2 equations. And yeah, you can write out what is friction force. Friction force equals to mu n. N in this case can be found in equation 2. Can be written down as mu mg minus f sine theta. But we don't really know what is mu here. And that's all we can get from Newton's law. Now we can apply Euler's law on k direction, define positive direction, and find out which point you can use to define moment. Here we're going to use sum of all the moment about g. And this should equal to Ig alpha. That's a special case one. Now let's find out all the moment about G. Go back to your free body diagram. This is our G. And all the forces pass through G and would not contribute to the moment. So we have this normal force with force, they both pass through the point G. So we don't have to worry about these 2 forces. However, this F force and friction force will both cause moment about point G. And if you choose G, which is a special case one. And there's another approaches, you can also choose C. You can try that by yourself. If what happens if you choose C is all the forces passed through C would not take in consideration into the moment equation. So this friction force, wave force, also this normal force will all pass through C. So all you're left with is this F force. So actually, in this case, if you choose C, the calculation can be easier, since you only have to deal with this given F force. Now, if we're dealing with point G, we have to count the movement from this friction force. Like I mentioned, we don't really know what is mu of friction force. So that could cause some difficulties, but let me just write down the moment here. So the moment caused about G, and you have friction F sine theta, that's on the Y direction. Okay. The Y direction of F will pass through G, so that wouldn't cause standing friction. Instead, here should be cosine theta times small r, and the moment about point G gonna be positive, so that's positive, and another force gonna be friction force. So friction force gonna cause a clockwise friction force here, point G is here, gonna cause a clockwise rotation, so that is negative. So negative friction force times big R. And that will give you I G alpha. So that's one more equation we can get. And let me see. And in this problem, I think we forgot to mention, it's given the radius duration kg. So we know kg equal to 0.25. Like I mentioned in the last example, kg equals to Ig goes to mkg squared. So here we can rewrite this Ig as kg squared alpha. Okay, those are the three equations we find from Newton's law and the Euler's law. And however, we probably have more unknowns. What we don't know is this friction force, what is acceleration, what is normal force, and what is alpha. So we have more unknowns than the equations we have. That means we need to find one more equation. And how to find that equation? It's to use the no slip condition here. So this problem tells you there's no slip. So that can give us some useful information about acceleration of G. So use no slip condition that tells us AG goes R to radius. Let's use this instant center method and negative. It's rolling without slipping. And this will give you one more equation. And you can plug in equation 4 to equation 3. So use some of the 1, 2 into equation 3 to find the relationship about what is AG, angular acceleration. So in this problem, we try to find what is the alpha. And this problem can be related to what we learned in no slip and in instant center problems. Because if we can find the expression about AG, if you write down what is the symbolic solution for AG, going to be R cosine theta minus small r over m r squared plus kg squared. So if you get a symbolic solution for AG, and you look at how this theta would affect the direction of AG is. If theta equals 0 degree, which is horizontal, then you end up with positive AG. So AG greater than 0. If your theta is 90 degree, now our AG gonna be less than 0. And if your theta equals to first r small r over large r, then you're gonna have AG equals 0. So the theta tells you how you pull this would affect which direction the spoon will roll. And that's something we did in that's chapter 2 topic. Right? Okay, that's all about today. And there's 2 examples, and hopefully those 2 examples can be helpful for your homework. All right, that's all for today. Thank you, guys.